Do you know what the sun is made of? We can't go to the scorching star and take samples as we did with the moon, but there's a way to do that without traveling so far away. Rainbow can help. Well, not exactly the rainbow we see after rain showers, but the spectrum of light. To be more precise, the Fraunhofer lines. So these lines are like those mysterious dark marks that show up in the spectrum of stars, just like our very own sun. They happen because certain gas elements in the atmosphere selectively absorb the sun's rad vibes at specific wavelengths. The first person to spot these lines was an English physicist named William Hyde Wollaston back in 1802. But it was this German physicist named Joseph von Fraunhofer who really owned the scene and got these lines named after him. He plotted over 500 Fraunhofer lines and even gave the brightest one some snazzy letters from A to G. And we still use those letters today. As we speak, there are about 25,000 Fraunhofer lines that we know of in our solar system spectrum. Now, let's talk about the three types of spectra you gotta know about. First up, we've got the continuous spectrum. Picture all the colors of the rainbow, all the wavelengths of visible light with nothing missing. It's what happens when white light gets spread out by a prism. Next, we got the emission spectrum. When atoms get all jazzed up and excited, they start splitting out the light. Different elements have their own signature wavelengths, like their own funky colors. Sodium goes all yellow, neon rocks red and orange, and mercury brings blue and green vibes. It's like a fingerprint or a barcode for each element. So, if we can measure the wavelength of that light, we can totally identify what element is getting down. Lastly, we've got the absorption spectrum. Imagine this: white light with all its glorious colors passes through a gas, but when it comes out on the other side, some colors are missing. Why? Well, the atoms in the gas snatch up light at specific wavelengths, the same ones they would emit if they were all excited. So, what we see is a continuous spectrum with these groovy black lines on it. When we pass sunlight through a prism, we get the visible spectrum we expect, but also a bunch of those black lines. Those over 600 black lines are caused by chemical elements in the sun's outer layers absorbing specific wavelengths of light. So, if we measure the wavelength of those lines, we can figure out what elements are hanging out in the sun. And by looking at their intensity, we can even get an idea of how much of each element is there. It's like putting together a super cool puzzle to learn what the sun is made of. There was this set of lines, including a strong yellow one, that didn't match any known element. In 1870, a scientist named Norman Lockyer suggested it might be a totally new element, and he named it helium after the sun deity Helios. 25 years later, helium was discovered right here on Earth. Scientists can gather all the details about materials on Earth and in space just by looking at their colors. It's all thanks to spectroscopy. This technique works because light and matter have a special connection and behave in predictable ways. So, we've got gamma rays, X-rays, ultraviolet light, visible light, the colorful rainbow, infrared light, microwaves, and radio waves, all different types of light, also known as electromagnetic radiation. Together, they make up what we call the electromagnetic spectrum. Even those radio waves that bring your favorite tunes to your radio, the microwaves that zap your leftovers, and the X-rays that dentists use to spot tooth decay, they're all forms of light too. Light has some pretty interesting characteristics that come in handy for spectroscopy. First off, it behaves like a wave. You've probably encountered waves before. Think water ripples or sound vibrations that tickle your eardrums. Well, light waves are similar, but they're a bit peculiar, like me. Instead of causing matter to move up and down or side to side like mechanical waves, light waves consist of electric and magnetic fields that jiggle perpendicular to each other. And while mechanical waves need matter to travel through, light waves can zoom through empty space as well as matter itself. Now, let's talk about wavelength, a fancy term for the distance between wave peaks. For light waves, it's the distance between those peaks in the electric and magnetic fields. You're actually super familiar with the concept of wavelength already. You see, your eyes can perceive differences in wavelength as differences in color. Shorter wavelengths appear bluer, while longer wavelengths give off a redder vibe. So next time you're admiring a vibrant rainbow, just remember you're actually appreciating the various wavelengths of visible light. Now here's the deal with spectroscopy. Different stuff emits and interacts with light in different ways, depending on things like temperature and what it's made of. We can use spectra, which are like fancy patterns of colors, to figure out cool things like how hot something is and what elements and compounds it's made of, without even touching it. Now, first things first, we gotta separate light into its component colors to make a spectrum. You can do this with a glass prism, a thing called a diffraction grating, or even a combo of both, which we'll call a grism. You know, those rainbows that pop up when sunlight hits water droplets? Yeah, those are natural spectra thanks to the water acting like a prism. Spectroscopes and spectrographs are the fancy tools scientists use to capture and measure these spectra. You can display a spectrum as an image, but if you really want to dive into the details and see all the little differences in brightness between colors, you gotta plot it on a graph. A spectrum graph can reveal stuff that our human eyes can't catch, like tiny variations in brightness and wavelength. All spectra show pretty much the same thing, how brightness changes with wavelength. Scientists like to classify spectra based on the way light and matter interact and how they use them. Let's start with the continuous spectrum. It's just what it sounds like, continuous. The brightness flows smoothly from color to color, and in a perfect continuous spectrum, there's no missing colors. There's this thing called a black body curve, which is a type of continuous spectrum. It's the range of colors that an object, like a star or a light filament, gives off based on its surface temperature alone. Super handy, because the shape of the curve and the peak wavelength, the brightest color, tell us about the surface temperature and nothing else. Hot stars are bluer, while cool stars are redder. The continuous spectrum is also a great starting point for other types of spectra, like say hello to the absorption spectrum. It looks like a continuous spectrum, but some colors are way dimmer or even missing. Those missing colors show up as black lines called absorption lines. And guess what? They happen when starlight passes through stuff like dense gas, and the atoms and molecules in that gas absorb certain wavelengths. Each element in the gas absorbs its own special pattern of wavelengths. So if you recognize that signature pattern, you know that element or compound is present in the gas. The darkness of those absorption lines tells you about the amounts of each material as well as the temperature and density of the gas. Remember how we said stars emit a continuous spectrum? Well, turns out that's not entirely true. If you take a real close look at the sun spectrum, you'll see lots of absorption lines. Each one corresponds to an element found in the sun. Some of the light generated by the sun gets absorbed by atoms in its cooler layers as it travels out into space. We know what the sun is made of because of its absorption spectrum. Now, my own personal absorption spectrum would indicate the presence of a large quantity of chocolate.